interacting with the world again. They feel cut off. They're the same as you or I. They have the same goals and aspirations, and they have no limitations in their brain. They just have limitations from their body. So all of them are extremely excited, very happy. They want to move again. I mean, that's the greatest goal, is to move again. And we have to be very careful, of course, not to promise too much.
I see. Well, of course, our audience is intensely interested in codes and cryptography, and you're cracking one of the most interesting codes in existence, the neural encoding of the brain. So you talked a little bit about your efforts in constructing the current generation of BrainGate. As you work on future generations, what is the frontier? Where do the challenges lie? Is it a matter of the scale of the problem, or are there actually qualitative differences as you begin to incorporate new features?
Well, it is an immense problem. If it's one of those things, if it was an easy problem, we would have figured out how the brain worked a long time ago. It's a very complex problem, and we don't know really what these spiking signals actually mean. They are the brain's code. We are developing a kind of encyclopedia, neuron by neuron, of what they do. How do they get involved in hearing or seeing or moving? And we know that they have common features, but we just don't understand the way that transformation occurs from integrating huge amounts of information into some kind of spike train. We have just the beginnings of that understanding.
I see. Well, BrainGate restores lost capabilities to patients who are suffering from a dysfunction. But as you've shown, it's possible to control more than artificial limbs. You showed, for instance, the ability to control a cursor. Can you envision a day when healthy patients have implants of this sort to supplement their functionality in the world? I don't know, implants that help people stick to their diets, or control devices for a third arm, or something along those lines?
So there are many people who think about these kinds of things, that they want to be able to extend their capabilities. So the first thing, this is a medical device. We're trying to develop something for individuals who have disabilities to make their lives better. The biggest barrier is this does require brain surgery, so we don't take that lightly. It's something that is always raises a concern. Where we will go with this and how we will use it, I think, will require serious debate and serious discussion. But as I said, I think the barrier will always be the surgical one, that we will not, in any cavalier, implant able-bodied people to have sort of frivolous functions. On the other hand, we have many things already available that are aids. We all have smartphones that carry around that are a substitute for our memory, because we can't remember telephone numbers and things. So we have many, many devices, and so it would have to be clear that at some point we would outstrip all of the available external technology to ever even begin to think about enhancing us by implanting something in the brain.
Well, have you in fact been approached by industries or companies or government agencies who are hoping to exploit BrainGate for purposes other than the strictly medical one?
Yeah, I wouldn't say exploit. I think that I mentioned this EEG-like signal that is available from outside your head, so there's a lot of people interested in how much control can you get from that. And in fact, it is a very noisy and very hard to manage signal, and it's not very reliable. So there are a number of people who would like to see that signal be as good as the one you get from inside your head. It's not going to be, I think. If you could, well, let me tell you, there's one place where it's actually being, there's a great deal of interest, and that is in the toy industry. You can get a little bit of sort of, are you thinking, are you more aroused, are you happier, or are you a little bit more relaxed? You can pick that signal up with a very simple toy-like device, and so for gamers, this will be a fun toy. And there are a couple of companies already making devices that I think will be out this Christmas. So that's something that will be around.
Well, are there frivolous or dangerous applications that you're afraid of seeing?
Well, the use of BrainGate requires the participation of the user. So if you don't want it to work, it won't do anything. You have to actually participate in the use of it. So we're not too worried about that. But as I said, there are people are always trying to say, where will this go? And I think they draw from the science fiction movies. As I said, the kinds of interfaces that you see in Picard, for example, that kind of integration of the machine and the human is really extraordinarily far off, because we can't, tapping into the nervous system is very difficult, and taking signals out we don't understand. So we have an extremely long time before we're at any level like that.
So it may be a little early for me to ask this question, but as the technology evolves, what are some of the first ethical quandaries that you foresee?
In terms of the patients, one thing, these are not big ethical quandaries, it's about paying for them. They can be very expensive, but we have models of how to pay for expensive devices, but how do you decide who gets them, those kinds of things. So if there's a person who doesn't have the means to pay for it, and a person who does, then who decides who gets the technology?
Okay. Well, let me ask some questions that may relate to the technology as it will appear in 10 or 20 years. But, well, actually, let me ask a question about what you could do today if you were given ample enough resources. So if we gave you a $10 million grant and, say, liberal surgical access to patients, could you build an infallible lie detector? Is that within the realm of possibility?
No, because we don't understand the basis of lying and those kinds of... So we're looking at very simple functions, like left and right. Very, very simple kinds of control. So we can understand those. There are a few places in the brain where we can get some insights into your thought processes, but they're really only a guess. So we're sort of guessing, and sometimes we're right, but we always... Whenever we tap into single neurons, we always have some probability of being wrong. And we have nothing like what a lie is. We have no concept of what the neural representation of a lie would even look like. So as I said, it's hard enough to know. We're working at what does a neural representation of a spot of light look like? What is a representation of a tone, a sound? A word is beyond our thoughts currently. What is the neural representation of a movement? You heard a little bit of what that sounds like. But putting it all together, the assembly problem is the big one that's a huge barrier. And I think what we need is, this is where science plays a big role, where for the first time, listening into the human brain, the thinking, acting human brain, and we're actually able to ask, what's going on in there? We can actually ask the participants, what are you thinking about? And we can get some clue about what the activity is. Interestingly, if you ask Matthew, what is he thinking about while he moves the cursor around, he'll make up a different story every day. It's sort of the same kind of story that if you said to a little kid who gets up and brushes their teeth, what did your brain tell your arm to get your toothbrush to go up to your mouth? They don't know. It just works, And so pretty much that's what happens. They somehow think about moving, and the cursor will move, the events unfold. And we've even found that if people begin to come up with too crazy a strategy, that it begins not to work so well. They just have to let it flow naturally.
Well, one thing I would love to see would be an external projection of dreams, as it were, right? a movie rendering. Is that simply off the books, or is it conceivable that someday we'll be able to do that?
So you are actually bringing up an issue that's something that is looked at. So it is known that if you do something, I'll give you a sense of how primitive our knowledge is. In rats, if you have a rat run around a room, there's a little part of your brain sort of deep buried on the inside that unfolds a map of space. And what each little neuron says, I'm here, I'm in the next spot, I'm in the next spot. And when the rat goes to sleep and dreams, it replays the sequence of where it ran. So you can actually predict that if the rat ran across the stage here and out the door, and you replayed its dream, you can actually reconstruct that from the activity that they have in their sleep. But that's a long way from projecting your dreams of whatever you dream about out into solving cryptography or something, onto a projection screen.
Well, bringing the line of questioning perhaps a little closer to reality, I'm sure many in the audience are wondering about the application of this technology to information security. For example, do you think that brainwaves are distinctive enough to identify individuals to computing systems? Could they ultimately serve as a replacement for biometrics, fingerprints, for instance?
Yeah, there are. I think the variability is so great, and it's also the reliability of detecting the signals. That is, you can't just put your head in a dome and get in a simple structure and get a good signal. That is, it's very sensitive to exactly how you set it up. Mm-hmm. So there's a lot of variability just from that. And then in individuals, I think it would take a pretty sophisticated system to see whether there's a neural signature. But we do know already, for example, there are some people that have a potential in their brain, It's called a P300, but it's a surprise potential. If I show you something and something pops up new on the screen, you have this little electrical potential that pops up. You can record it even from the outside. But it's not that reliable, and about 15% of people don't even have it.